Thank you very much, Luc, for this very kind introduction. And I want to thank Luc and the organizing committee to inviting me to give that open lecture. That was a very kind gesture. It's very good to be back home after 22 years. I hope you're enjoying Nantes as much as I do. The city has changed a lot in 20 years, I can tell you, but it's really astonishing. So as Luc mentioned, I kind of stepped away somewhat from offshore geotechnics, and I found myself very fortunate to work in my position with a broad range of people from very different disciplines. And about 8 years ago, I took an interest in wave energy and starting to work with a local developer called Carnegie Clean Energy, based in Perth, but now with headquarters in Spain and in Ireland, and developing their technology under the European Commission program. Through that journey, I created Marine Energy Research Australia, which is a research center within the Ocean Institute that encompasses all the research on ocean renewable energy. And I thought that would be a good opportunity to showcase a bit what energy can deliver, what wave energy can deliver. So wave energy is a new gold rush. It's obviously a bit provocative, but somewhat a reflection as well of the journey over the 20 years of the ISFOG conference. And if you look at the number of papers on offshore wind in 2005 and you compare that with the numbers today, you'll see obviously a very prominent trend. And imagine if 20 years ago somebody had presented an open mind lecture on wind energy is a new gold rush. Would you have believed it? So stay tuned, because there will be another provocative statement during this lecture, and so we'll see if you can spot it. I may just start by a few principles on wave energy in case you're not familiar. So when the wind is blowing over the oceans, over hundreds and thousands of kilometers, it creates ondulation on the ocean, which is characterized by a period and a wave height. And so the orbital motion of the ocean particle have kinetic and potential energy that you can transform in electricity through various systems. The power, as mentioned, is a function of the square of the wave height and of the period, but the power you can actually capture from the wave, it's actually a trickier exercise. It's a function of various parameters, including the wave stiffness, wave spreading, and so on and so on. But the big advantage of wave energy is that it's actually a very consistent and statistically predictable resource, as opposed to other renewable energy sources. And it's also a very high density, which means that basically you can concentrate a lot of energy capture within a much smaller footprint. So wave energy is actually not very new. The concept emanated actually from a French guy called Girard in 1799. He actually patented the concept at the time. And it's another Frenchman, Bessot-Bilousec, in 1910 that actually created the first wave energy converter, a 1 kilowatt converter that he used to power his factory at the time. But it's only from the 1970s that there was a renewed interest for wave energy with the oil crisis in 1973, and that various researchers and developers came up with various technology types, and you can see some of them here. What we call the point absorber, basically that has an anchoring point that is a floater at the wave surface or slightly below, and an anchoring point at the seabed that serves both as an anchoring point and a reaction point to create energy, but also oscillating water column, inverted pendulum, attenuator, and so on. And so I think, again, the second advantage of wave energy, as opposed to wind energy for some instances, is that you won't see a convergence of the technology like you've seen for wind, converging through the free blade towards the free blade systems that we are all familiar with. There is a huge variety of wave energy systems that caters from the watt to the megawatt, and then can cater to various markets. And so all the way from grid connection to power homes to actually regional community islands displacing diesel, and also ocean sensors, and so on and so on. And that's another advantage of wave energy that we will be exploring. As Luc mentioned, so I'm part of the International Energy Agency. So if you are not familiar with the body, so the International Energy Agency does a lot of prospective analysis. One of their key reports is the one on the net zero roadmap to achieve net zero by 2050. And an important message out of that report is to understand actually that 75% of the technology which is needed to reach this net zero by 2050 doesn't exist yet. What does it mean? It means that we are actually not going to achieve it with wind and solar and nuclear power alone. We'll have to develop new form of technology, and wave has a role to play in the future energy mix. Within that body, there is a lot of work being done, and so one of the subsequent prospective analyses that has been undertaken by Professor Henry Jeffrey from the University of Edinburgh is try to understand, the market demands and the economical benefits of wave energy being developed. And so you've got some numbers here. We talk here about all ocean energy, so it's wave and tidal. And so by 2050, it is predicted that we will have about 300 gigawatts of installed capacity, creating 680,000 jobs, adding $340 billion in gross value to the world economy, and capturing 500 million tons of carbon of CO2 every year. So 500 million is 0.5 gigaton out of the 37.2 that we are emitting every year. So that doesn't seem a lot, but still, it's 50 times more than CCS will ever capture, and for an investment which is at least, one order of magnitude. Did you spot the provocative statement here? I hope that's going to fuel some interesting conversation at the tea break here. So where are we in terms of technology? So technology has been evolving, following somehow a quite challenging pathway. Developers have been working very much in silo, protecting technology with IP and so on, then going under administration, all the lessons learned were lost, and so on. And so unfortunately, the technology has not evolved as rapidly as what we've seen in wind and in tidal, but has reached now levels that are close to commercial development. The most advanced one is probably Core Power, who has a point absorber deployed in Portugal over the last year that was connected to the grid, a 600 kilowatt point absorber. Carnegie Clean Energy, which I mentioned earlier, has won the Europe Wave contest in Europe and is going to deploy in Bilbao in September this year, a 1.5 megawatt wave energy converter. And actually in Australia, we had a development 3 years ago by Waveswell, who developed a water oscillator column that was deployed in King Island, a small island north of Tasmania, and that has been connected to the local microgrid and actually provided power over a year to the local community. But we are not seeing yet large-scale commercial development in the way that we are seeing for wind, and that we will see for tidal very, very soon. Nevertheless, there is actually a pathway for development and deployment over the next decade, and so with about 160 megawatts of ocean energy being deployed in Europe over the next decade, and about 25 of them is going to be wave energy, with one actually, again, Core Power, developing the first farm of wave energy converter in Ireland for a 5 megawatt capacity. So let's bring that to the Australian context now. And in collaboration with the Blue Economy CRC, Cooperative Research Centre, which is a 10-year industry research collaboration in Australia that has a strong focus on aquaculture and ocean energy. The team at the Ocean Institute at Almera has developed an Ocean Wave Energy in Australia report that presents the potential of wave energy in Australia, the technological pathway, and the hurdles that needs to be overcome to actually achieve its full potential and provide recommendations for state and federal governments. In Australia, we're extremely blessed because we've got the best wave energy resources in the world by a long shot. You can see here that the potential capacity is over 270 gigawatts. It far exceeds, what is needed to cover the domestic consumption. And a second advantage is that most of these resources are actually located on the southern coast, where we've got essentially the density of the highest density of population. In Albany, that we'll talk a bit later, we have the best wave energy resources in the world, about 50 kilowatt per meter of wave all year long, very consistent with very small variability. But that's not all. That's not the whole story. The potential of wave energy is not only the resources, the energy density, and so on. Most importantly, it is the complementarity to the other renewable energy resources. And so our team, again, has been doing a bit of work, started locally, looking at Australian city along the coast of WA and expanding to the whole Australian context to understand the impact of bringing wave energy into the energy mix in complement to solar and wind. And that's what you see here for 3 cities, Albany, Margaret River, and Geraldton. And so you've got the solar in yellow, the wind in orange, and the wave in blue. That is compared to the seasonal demand. And as you can see, solar plus wind alone can't meet the demand. For that, you need to add permanent storage, which is expensive and which is difficult. Once you start adding wave energy into the mix, the complementarity of the energy profile between the 3 resources actually lead to meeting the demand on a monthly, on a daily, and on a seasonal basis, and in most of the case, without any need from permanent storage. To achieve that, you need obviously to vary the proportion and the distribution of how much wind, how much solar, and how much wave we've got. But I think it's a very compelling case about where wave energy can actually complement over renewable energy profile. The second, behind that, you know, behind this simple resource assessment, we've done as well a full economical analysis. And that's actually a very important thing, because in the mix, you understand here that wave energy doesn't need to compete in price with solar and so on, because it actually provides energy when solar and wind can't. What it needs to compete with, it's with permanent storage. So you can actually accept a higher levelized cost of energy for wave energy that you can achieve with solar and wind and still end up with an energy at the end of for the whole system, which is very competitive. So as I mentioned, you know, the analysis has been done at the domestic level. And so one of the things that came out of that report and one of the principal recommendations for the federal government is to actually consider strategically wave energy into the energy mix. Because as you can see on the plot on the right, once you put wave energy into the mix across all Australia, you can save an equivalent of $20 million per megawatt produced of permanent storage into the mix. So where does it leave us? So that brings us to what we call the Albany M4 project, a project which I've been very privileged and fortunate to lead, assisted by Dr. Hugh Walgamot and Dr. Vibke Billing, who is the Center Manager of Marine Energy Research Australia in Albany. And so we had this crazy idea about 4 years ago to actually design, manufacture, deploy, operate, and decommission a wave energy demonstrator. We've done that in Albany, as I mentioned, that has the best resources in the world. It's about 500 kilometers south of Perth on the Great Southern Coast, a beautiful spot, and that has the advantage of having both a very, very high energy site, where you can actually deploy a full-scale wave energy converter to produce energy at the megawatt scale, but also a nursery site, which is simply a kilowatt scale, but which is very good for demonstrator purpose. So we've decided to deploy what we call the M4 wave energy converter. This is a design that has been developed by Professor Peter Stensby at the University of Manchester. It's what we called a hinge attenuator line absorber. It's a very simple device. It's a one wavelength device, and as you can imagine, there is a rotation in the middle, and so when the float at the front and at the back are actually on the crest of the wave, the middle is at the front, and vice versa. And that rotation at the hinge can be captured to transform, again, kinetic energy into electricity. The project motivation were very simple. I mean, first, to advance the technical readiness level of the device from 4 to 7, 9 being full commercialization, but also to demonstrate the local capability, the capability of the local supply chain to undertake a fairly complex engineering project, which I think is important to give confidence to potential developers that it can be actually achieved in Australia. In addition to that, we're actually collaborating with the local aquaculture company, and so and to demonstrate the potential of wave energy, and we are running virtual macrogrid exercise to understand how bringing wave energy can help them decarbonize their industry. And eventually, the main objective, in a sense, is to advance the whole industry. I mentioned earlier, you know, that progress have been slowed down and made challenging, you know, by the silo mentality between the developer. And so with M4, which is IP-free, We're actually doing here what is the world's first fully open access wave energy demonstrator, where all data, including power capture and power efficiency, will be actually made public and available to everybody, with the hope that we can advance the whole industry with this. Some metrics here very rapidly. You know, it's 24 meters long, 42 tons total ballasted, two times 5.5 kilowatt generator, so 11 kilowatt capacity in total. Done 80% locally, quite an important point because it was funded partly by the state government. And with a strong community engagement to work on the social license of ocean energy, which can or cannot be a challenge. It is definitely one in Australia, having worked with the federal government on the public consultation and social license for offshore wind development in Bunbury. It has proven to be extremely challenging. It's a nearly $5 million cash project with another probably $5 million of in-kind and many sleepless nights. So $10 million and 12 partners with UWA being the lead, but working with multiple institutions across Australia and in the UK, notably the University of Manchester. So why M4? So first, as I mentioned, it's IP-free, so we can publish everything about it. And actually, if something is excited by the technology, you can come up and take it over and develop it to the next level. You're more welcome. It's been optimized heavily through lab testing for low levelized cost of energy. It has been also optimized for survivability, maintainability, deployability, simplicity, and it's scalable from kilowatt to megawatt. And I'm going to use that example to kind of debunk some of the prejudice of sort that people may have about wave energy. You know, it's too complicated, the ocean is a too harsh environment, this is never going to work, and so on and so on. So let's look at optimized LCO. So you've got here the device in a front view. And so what you see in the blue, it's actually the gearbox here. So remember the device is floating, is flexing, you know, and so we've got the 711:1 gearbox ratio. That in turn power a generator. From that generator, you get electricity that you put in an AC-DC converter that eventually goes to a supercapacitor to smooth the profile, because obviously, you know, it's an intermittent energy input, and then eventually that wind up into a resistor. We didn't have the budget to put a cable to shore and connect that to the grid. That will be the next step. And all of that is controlled locally by a computer, and notably that enables fine control of the power takeoff to optimize power capture. So what we've got is that we've got an input from the generator. The electricity generated is actually directly proportional to the torque in the gearbox, as I mentioned. Then we dump that into the supercapacitor to smooth the energy profile. When it reaches a cap, it's dumped into the resistor, and eventually this is the resulting power profile that we've got. The power profile here is actually for the moderate sea state with a significant wave height, about 0.8 meters. But at that significant wave height, we ended up generating a peak power of about 9 kilowatts and an average of about 1 kilowatt, slightly below 1 kilowatt, which is actually very promising, and I'll explain why later. Another aspect of it is survivability, you know, and so lucky were we that on day 10 of the deployment, we experienced the actually highest significant wave height in the site, about 2 meters, so maximum wave height is about 4 meters, and an edge angle of about 40 degrees. And the device actually survived that extremely well without any technical issue at all, and has been experiencing over a rough weather like that over the 6 months of deployment. Another advantage of it is the maintainability. We've got all the power takeoff and all the electronic, as you see, 2 meters above seawater. The photo you see on the right is actually the splash under this 40-degree hinge rotation, and that just barely basically touch the base of the passageway and all the electronic. And it's a very important aspect. Just to put some context, on the 13th of March, we had the highest rainfall in Albany ever recorded. And the record started in 1887. And that resulted, for those who are familiar with Australia, this is Middleton Beach completely flooded. And so that resulted in a failure of the data module. But no drama, because we could simply just jump on the Zodiac, go to the device, get up on the passageway, open the cabinet, and actually that was just a small leak of water dripping from a single boat that was basically not totally sealed and that was dripping off the data module, and we had just to switch it back and be back in operation immediately. Another advantage compared to other devices, for example, that may have the PTO submerged underwater, which make maintenance very difficult. Deployability is also a very important aspect. I couldn't talk about it without mentioning the anchoring system. Very simple anchoring system, a 10-toy floating buoy connected with a single riser to 2 clamp weights, 2.5 tons, and then to 3 1.5-ton anchor, 20-ton mooring capacity, and you see here some of the photos of the device deployed. If there is one thing that we learned from that project, which I'll explain a bit later, is that it's actually the need to revisit the regulation and the code because this is highly over-designed. And so it's a 20-ton mooring load, the highest load that we have ever measured, even in the condition that we just saw in the video, has been only 3 tons. Deployability, it's an accelerated video of basically a small boat coming to tow the device back to shore for a bit of maintenance. Within 30 minutes, you can unhook the device from the mooring buoys and bring it back to the marina. It is as simple as that. We've been measuring a lot of data out of this device, hydrodynamic performance, power generation, power distribution, marine growth, mooring response, and marine noise. The device was taken out of water on the 30th of April, so it's very new. We are simply starting now to look at the data. You can see on the plot here the trajectory, the positioning of the converter, across a full day, depending on the wind, current, and wave condition. And so that's going to result to a lot of academic publications, but also on reports to state government and stakeholders and the Blue Economy CRC about what we learned from that. And one thing we learned, which I thought was very interesting, is that everything worked as predicted. And so that may seem quite underwhelming, but it's actually quite an important result. And it validates the approach that the M4 device has been following, which has been focusing on the technological performance level rather than the technological readiness level, which is the pathway that most of the previous developers have been followed. And the problem with the TRL path is that you need to engage very high capital immediately to put a device in the water and test it again and again and again. Well, when you follow the TPL curve, you actually do a lot of lab testing beforehand and go to the water only when you have gained enough confidence and understanding about how your device is working. And I think M4 is a very good example of that. What you see here is the RAO for the hinge rotation and the comparison between prediction and what we measured. So what we learned, and so very briefly now, so there is a lot of room to optimize the design, and again, this is a call to revisit, the regulations. BMT was our partner into that, did everything by the code using DNV regulations, and so there is room to optimize everywhere. And so I think if we want to reduce the levelized cost of energy, this is something that is necessary. Regulations that cater for the very specific characteristic of wave energy converter as opposed to general offshore engineering design. Another thing which has been very satisfying is that the local capability. Albany is a small town, it's 30,000 people, and yet, we found everything locally. It was manufactured locally, deployed locally, and so on. And so we've limited upskilling, but it's actually benefit extremely well the local community and the local business. It is a higher cost, but it has proven to be the right choice. The PTO is actually the only thing that was produced externally, and so we ended up having so many issues with them that the extra cost associated with that was very significant. So I think locally is always a good advantage. Very strong support from the local community. We had engaged very early in social licensing, and that has proven to be very important. As I mentioned, 12 partners, the importance of partnership, and have a very good risk management plan, because obviously nothing went smoothly, as you can imagine, even if the story sounds nice at the end. Next step, and that was the whole purpose of that project, is what, again, raise the potential, raise the awareness of wave energy in Australia, and bring the community and the industry along. And so we are in collaboration and in discussion with 2 developers, the first one being Motion, who has developed the Blue X device in EMEC, European Marine Energy Center in Orkney, and so now wants to bring to Australia and understand how it behaves in actually tropical water. So we're going to go from 8 degrees in Orkney to 21 degrees in Albany, and eventually to 31 degrees on the Northwest Shelf, and understand aspects associated with marine growth and hydrodynamic performance under our wave conditions. And the next one as well is WaveX, which is a local developer as well, which has been awarded recently $2.5 million to deploy in Albany in collaboration with us and with the Norwegian Geological Institute a DSPAR system. And so we hope to be able to deploy that this summer, or probably most likely the next summer. And so that's going to be the opportunity for me to talk a bit about geotechnique, although Luc has forbidden me to do so. But within that project, we are going to explore the potential of helical anchor from local company. Local aquaculture use helical anchor extensively to power mussel nets and that are 140 meters long. And so they have developed the technology and the capability to use helical anchor. And if you looked at the proceedings of the conference, you'll see that we've got a fairly large helical anchor research program that is championed by Giuliano Nitet, who is going to present a bit later this afternoon. And so Giuliano will be championing, in collaboration with Pierre at NGI, the development of helical anchor for this project. And that's all for me. I hope you've been convinced about the potential of wave energy.